This is a classic 65mm wood frame. And this is a 3D printed canopy in PLA. And this is a 3D printed wood frame. And it doesn't break. It doesn't break because this is made of TPU, which is basically rubber. Although rubber is very soft. And the question is, can it also fly?
Hey, welcome to my channel. My name is Shah, mechanical engineer by day, drone builder by compulsion. I spent 4 years deep in this hobby. Building, flying, crashing, repeat. Then life happened and I took a 3 years break. And a few weeks ago I came back. Started where any sensible person starts after a long break, on a simulator, getting the muscle memory back, reminding my thumbs what they are supposed to do, and now I'm ready. Real drones, real air, real consequences. Coming back after 3 years, I did my research. And honestly, not that much has changed. The biggest shift is digital FPV system finally taking over. And for someone who loves cinematic footage, that's generally exciting. But one thing that hasn't changed is this dream that's been floating around the community forever, the indestructible frame. Something you can slam into the wall, pick up and fly again. And if you could print that frame yourself at home on your own printer, that would be, let's say, the ultimate wish of basically everyone in this hobby. The problem is that 3D printing has always had the reputation of producing weaker parts compared to injection molding. That's exactly why almost every whoop on the market used injection molded guards and canopies. Even injection molded parts aren't really indestructible, they're just the least bad option we've had. But what if that's finally about to change? People have been trying to make 3D printed FPV frames since the very beginning. Since the days when both 3D printing and FPV were things you did in your garage and explained to confused family members at Christmas. And there are some genuinely good design out there, but every material choice comes with a trade-off that's hard to ignore. PLA, cheap, rigid, easy to print, also shatters like glass, especially in the cold. Not great for a hobby where crashing is part of the deal. PA6CF, nylon with carbon fiber feel. Much tougher, almost as rigid as PLA, but the price jumps significantly. And it's still brittle enough to disappoint you when it matters. PETG, the compromise. More impact resistant than PLA, easier on the wallet than nylon. Better, but still not built for serious crashes. TPU, practically indestructible, absorbs everything, which is exactly why it's everywhere in FPV already. GoPro mounts, soft dampeners, whoop guards, but as a frame, too flexible. A drone built from standard TPU flies like something has gone very wrong. So for years, the 3D printing community has been stuck. Rigid materials break, flexible materials are too soft, nothing hits the sweet spot. And then BambuLab released a TPU specifically designed for their AMS system. And this one is different. It has a shore hardness of 68D, which if you are not into material science, means it behaves almost like a rigid plastic, but it doesn't crack. You can flex it, impact it, throw it at a wall, and it just comes back. It's also generally affordable, and if you have a bamboo printer, it runs through the AMS without drama. And that's when the idea hit me. What if I use this to build a whoop frame? Not a flexible, bouncy, wet sock whoop, a proper, rigid, structured whoop that also happens to be unbreakable. 68D sounds like a great number, but what does it actually mean next to the materials we just talked about? I don't do feels about right. I do data. I printed 4 identical specimens, one in each material, and put them through a 3-point bend test. The idea is simple. Simulate the load the frame would experience in real conditions. Using 1 Newton, or roughly the thrust each of my motors generates, and measure how much each specimen deflects under that load. On the epsilon axis, load. On the x-axis, displacement. You want to be as left as possible. PA6CF, competitive, and then the TPU for AMS, which turns out to be roughly 8 times softer than PLA. On paper, this thing should fly like a wet noodle. And yet it flies. No wobble, no abnormal vibration, exactly what it's supposed to do. The secret is the truss structure. Instead of making the frame 8 times thicker and heavier, the geometry converts bending forces into compression and tension along each strut. The direction materials are naturally strongest. Think of it like this. You can snap a pencil by bending it. Try crushing it lengthwise and it's completely different story. It's not a new idea. The Eiffel Tower, every bridge you've driven over, every aircraft wing, all trusses. Engineers have been trusting this principle for centuries. I just printed one in TPU. 2-inch props. Small enough for indoors, capable enough outside. Built around the popular 1102 with its 3 screw base. From there, the truss almost draws itself. Connect the motor mounts to the flight controller screw hole with struts in classic truss orientation. Posts and diagonals, nothing fancy. Then the simplest possible whoop guard outline around it. Just enough to test whether the weight and the rigidity were still in a sensible range. 3 wall thickness option, 1 layer at 4.26 grams, 2 at 5.65, 3 at 6.48. 2 layers had enough rigidity without unnecessary weight. Done. With that confirmed, the design got more detailed. A foldable camera holder, guards connected to the electronic stack, and these, what are called tentacles for now. The tentacles were designed to fold up and clip onto the motor mount, optimizing both weight and print orientation. Smart in theory. In practice, too soft to be useful and fiddly to assemble. Gone. Which led to better idea. Keep the frame flatter and add vertical truss posts to compensate. Stiffer, simpler, easier to assemble. The foldable camera holder went too, not universal enough. Replaced it with a fixed mount. Added some aggressive looking fins on the top to retain the receiver antenna and help with turtle mode. A VTX antenna slot, 2 screws beside the motor mount joining the 2 frame halves together. Full frame weight 18.22 grams. About 3 grams heavier than a standard commercial 85mm whoop frame. Time to build. The brain of this build, a Zeus 10 amp all-in-one whoop board, paired with Flywoo 1102 motors at 10,000 kV for a 2S build. VTX and camera go on after the first flight test. No point dressing it up before we know it flies. For props, at 2 inches, I could only find this Emax Ava Micro with an aggressive steep pitch. So I did what any reasonable person would do. I cut them down from 4 to 2. Custom props, very exclusive, very free. If you want to skip the build and jump straight to the flying, the next chapter is right there, but I'd be happy if you stayed. 4 long M2 screws go through the guards, doubling as a battery holder mount at the same time. Optional, but generally recommended, M2 plastic nuts on the bottom. Ultralight, and they stop the screws from sliding out at the worst possible moment, which during the assembly is always annoying. The flight controller drops in on its soft mounting rubbers. Twist the motor wires, route them through to the other side of the motor mount, bolt all 4 motors down. At this stage, they feel like they are mounted on a banana peel. Resist the urge to fix it, we are not done yet. Next, M2 metal lock nuts. I strongly recommend locking once here. Vibration will find and exploit any nut that isn't. These are generally difficult to tighten with bare fingers. A multi-tool works, proper tool works better. Top half of the frame goes on. Align carefully, then drive the 8 1.8mm thread cutting screws. I've used these exclusively instead of heat insert in plastic, and they consistently outperform them. Less drama, more holding power. Props on, pay attention to orientation. This is a pusher configuration, so the motor shaft enters from the top of the prop. Get this wrong and you have a very confused drone that goes nowhere enthusiastically. One red zip tie to hold down the receiver, because if you're going to compromise on tools, at least be stylish about it. If you skip the build, here's the ultra fast version. First problem. The original design was for a 1S battery. The 2S I wanted to run didn't fit the holder. So I cut it off and used the rubber band. Elegant? No. Effective? Absolutely. We move. Power on? No smoke. Always a good sign. Never take it for granted. Armed without drama. Yaw responds to stick input in the right direction, confirming the props are on correctly. Motor spin the right way. We have a drone. There is one thing I didn't love, the subtle metallic vibration in the motor sound. My suspicion is the hand-cut props. 2 blades I trimmed myself are never going to be perfectly balanced. I already ordered the proper 3-blade props, so we'll see if that clears it up. But the important stuff, power is there. Control feels good, and critically, no excessive vibration from the frame. No wobble, no oscillation, none of the symptoms you'd expect from a frame that's too soft. I know exactly what a soft frame feels like to fly, by the way. Guess how I know? The flyaway fear is gone, proof of concept works, time to refine. A dozen versions followed, each one a little better. Weight, geometry, guard shape, assembly logic, and then came the moment for the full build. Proper components, final frame, everything where it should be. I spare you the assembly this time. Ladies and gentlemen, meet the indestructible rubber 2-inch whoop. I'm calling it Roofy. What do you think? A proper name. It's so light it can rest on my rosemary, which is either a testament to the engineering or a sign that I need to get outside more. 3-blade props on, and that metallic tingle is completely gone. Smooth, quiet, exactly what it should sound like. Unfortunately, the weather has not gotten the memo about this video schedule, so the apartment it is, which honestly is where this drone belongs anyway. Light enough to fly between the furnitures, forgiving enough that when you clip a door frame, and you will clip a door frame, you just keep going. I did manage a few light crash tests indoors. Walls, corners, a couple of confident punches into the ceiling. No consequences, just expected. It took a long time to get here. The design iterations, the material testing, the hand-cut props era I'd like to forget. But the result is exactly what I set out to build. Something I can fly without flinching. The real test, outside, full speed, no mercy. That's coming in the next video. So this drone performed way beyond my expectation. It was smooth and responsive at the same time. Now there is one thing missing. The real test, the field test, and see how it behaves when it crashes into the concrete. Unfortunately, outside is raining, so we have to wait. But I promise you that it's going to come, and I will not be gentle with it. So if you don't want to miss this event, remember to subscribe. In the meantime, I will share the STL file of this whoop frame with you for free. The link is in the description, so you can try yourself if you have the TPU for AMS. If you like the video and want to support future projects, there is also a coffee link in the description. Every coffee keeps my printer running and the propeller spinning. See you on the field soon, weather permitting.